Okay, let's continue with the next lesson now. Oh goodness sake. Electromotive force and internal resistance. Got it on deck?
Yeah.
Yeah. Yeah. Now, that's kind of a new word for us, electromotive. Right, okay. So we've kind of mentioned this a little bit before, but potential difference, what precisely is it? So potential difference is just another name for voltage, really. And we talked about this already. But if you didn't get that, you should write it down. PD is used for short. So I could say, what is the potential difference? Or I could say, what is the voltage? Yeah. Now, electromotive force, also called EMF. We need to work out what this word means. So let's break it down. Electromotive and force. So what does the prefix electro refer to? Electricity. Motive?
Motion.
Like motion, and force is force. So what do we think electromotive force, or EMF, could be about?
The force caused by electrical movement.
You're saying, yeah?
Force by electrical movement.
Okay, and you were saying?
Basically the same thing.
Yeah. So you almost have it. It's actually backwards. It's not the force caused by electricity. It's actually the other way around. The meaning of this word is the force that pushes the electricity, so to speak. It's the thing that makes the electricity move almost. It's the EMF by an electrical source like a battery, for example, is generally defined as the electric potential for the source in a circuit. Now don't write, I'll tell you what to write down in a moment. A device that supplies electrical energy is called a seat of the electromotive force, or the EMF. EMFs convert chemical, mechanical and other forms of energy into electrical energy. The product of such a device is also known as an EMF. So, if I take the battery out here, we say that this has an EMF because it provides energy. It generally is defined as the electrical potential for a source in a circuit. So if I put this in a circuit, I call this part the EMF because that's what's providing the energy. That's also called the seat of the circuit. How does it work? The EMFs convert chemical or mechanical into electrical. So this here, I think, what is it? It's lithium? No. It's mercury and cadmium. So it converts that chemical energy into electrical energy. Okay. So you might say, what's the difference between EMF and potential difference? Well, the way I think about it is that if I say I have one EMF, 1 volt of EMF means each coulomb is given 1 joule of energy. So this gives a joule of energy to a coulomb. Whereas if I say a potential difference of 1 volt, I usually mean that each coulomb did a joule of work. So the difference for me is EMF provides and potential difference takes. But you measure both of them in volts anyways. So they're both a type of voltage. So an EMF voltage is a volt that provides, and a potential different volt is a voltage that takes. It's all really different. Now what do you need for the exam? 2 things. You need at least the second sentence. It's generally defined as the electrical potential for a source in a circuit. But you also need to say it is measured in volts. Okay, so the second sentence is enough. It is generally defined as the electrical potential for a source in a circuit. It is measured in volts. And if Chow was here, he would want to write the whole thing down. If you're watching this, Chow, you just need the second sentence.
Sorry, what is the second point?
As after you write the second sentence,
Yeah.
you add in, it is measured in volts. Do you have that? Yeah, you do. Andek?
Yeah.
Yeah? Right. Continue. So basically EMF gives. Okay. Now, the following circuit below is a very important circuit. I'll draw a picture for you here. This is my AAA battery. Out it comes again. One of these guys. Okay. Now, this is how we picture it. It's called a battery because I think, it has 1 or 2 cells in it. So, maybe we'll imagine there's like 2 cells in it, for example. We also imagine, oh sorry, I did that backwards, didn't I? Because this side is the positive and this is the negative. So the current goes that way in it. We also imagine that there's a little resistor in here. Now this is very important. I'm not saying there is a resistor in it. I'm saying it's like there's a resistor in it. What's the difference? It would be stupid to put a resistor inside the battery because you don't want to waste energy. Because remember we said a resistor, it reduces the voltage, it consumes energy. So it's stupid to say that we put a resistor in there. We imagine it's like there's a resistor in there because you know that batteries get warm, and because they get warm it means they waste energy. So the picture we have in our mind is this. We picture a battery having like a pure part, this part here, but then we picture it having a part that we don't want, the resistor part. But again, it's not like I'm saying it is like this. I'm saying we model or imagine it's like this. Do you understand the difference or not? Or am I confusing you? You get the difference, yeah? Are you sure? Yeah. So, is there really a resistor inside it? No, okay, good. Okay, that's the main thing. So, this part here provides the EMF. This is like the pure part. And this guy here, there's a potential difference. It wastes some of the voltage, producing heat. Okay. So it's actually really good to know how big this resistor is. It's called the internal resistance, and it's usually quite small. Fortunately, it's quite small. So here's the circuit that you can use to measure it. Here is the battery, the cell. Here is the pure EMF, and here's the internal resistance R. We put a voltmeter around it, and we put an ammeter, and we also put in a variable resistor. It should remind you of a circuit you did recently. What circuit is this reminding you of? From what lesson? Not Kirchhoff. Another lesson where we had a circuit like this, where we had a voltmeter, an ammeter, a variable resistor, a fixed resistor, and a power supply. There was another lesson that had a circuit very much like this. No remembering. The IV characteristic curve. Yeah. what is the effect of changing the variable resistor? It changes the voltage, and then we measure the current. Yes? You have the circuit there? Yeah, it's similar to this, isn't it? It has all the same parts. And you made your graph. Yeah, yeah. So we're going to make a graph again. Before we do that, I'd like you to draw this circuit. You got that? Is that a yes? I don't know. Is that a yes now? Yeah. So, yeah. Now, this is kind of an interesting question. It'll make you think. What is this voltage measuring? It's measuring the voltage around this, isn't it? However, that will be exactly the same as the voltage around this. There's a couple of ways to think about it, but you kind of remember, you know, if you have a power supply, let's say this power supply is 2 volts, then what is the voltage around the resistor in the circuit? It also has to be 2. The only exception to that is if you had another resistor, then we say that these two, they must add up to make 2. So that voltage here on the voltmeter is actually the same as if you were to put a voltmeter around the variable resistor. It's actually more usual in these circuits to put the voltmeter around the battery. It's convenient. Right, who shall I pick on? I will, because I want you to love Kirchhoff, learn to love him. And I think the person who hates him the most is Kim. So Kim, can you give me the loop rule, please? So I want you to start here. So we'll say the voltage here is equal to EMF. So let's begin. We have EMF. Okay.
Minus.
Yeah.
I.
Minus here. Yeah, what's this?
Resistor, is it?
It's a resistor, yeah. And what's the voltage here?
IR.
Yeah, we don't know the or, but we do know the I. But what does IR equal?
V.
V. And do we know the V? We can know the V from this. So we have EMF minus V. Good.
Good. No, minus.
Mm.
I.
IR. And we know the I and we can know the or. We don't know the or. Yeah, but we're looking for the or. So we can get this formula. EMF minus V minus IR equals 0. That's by the loop rule of Kirchhoff. Okay, so I'll let you write that line down first. Okay, so you got that? Yeah? Continue. So, you can use in the formula book, if you look in the formula book, they write this formula in the book actually as EMF equals V plus IR, I think. Actually, why don't we check? That's a good idea. Can I borrow your book for a second there? Just check. No, not quite yet. They write a little bit differently. So you can rewrite this. Yeah, just so you know, in the book they write it as V equals EMF minus IR. So I should write that down for you. In the book they write it as V equals EMF minus IR. I think I should change that here actually in my notes. Did you get that? Like this is how it's in the formula book. Okay. Right. Continuing. Thank you, Matt. Do you have that, Anta? Yeah. And you can write that, you can expand that even more, but I don't quite think you need this just yet. Yeah, I don't think I'll have you write that down. I should delete that, perhaps. Anyway. Oh, come on. Right, so I'll return to this. I want to talk about the graphs. Now, excuse me. In this formula, there are two things you know and two things you don't know. So what are the things you could know in this formula? If you look at your circuit, which things could you know here from your circuit? V, good.
I.
And I. And which things do you not know? You don't know the OR, and you don't know the E, the EMF. And those are things you would like to know about your battery. So, you have a choice. Sometimes they write the formula like this, and if they do, you could make this graph, where you can have V here, and I here. So this V is like the Y, and this I is like the X. And what way will the graph look? Because the minus here, the slope is minus R, so what shape is that? Going down. And where does it start? At E, good, yeah. Yeah. At the top, and it goes down. Like that. And what's the slope of this equal to? Minus R. Yeah, because the I is the X and the R is like the M. So, just like with the IV characteristic curve, having this graph is very useful because it lets you find something which you can't find, which is the resistance. Because remember I said, it's not like there really is a resistor inside it that you can just take out and examine. But we're able to measure what the internal resistance is like. It's equal to, R is equal to minus the slope here. So that's very useful. Now sometimes, in the exam, they want you to write the formula the other way, where you have the I as the Y. So if I rearrange this, I could get I or equals E minus V. So you can get I equals E over R minus 1 over R V. Like that. Did I do that right? I did, yeah. So I here and V here. And this is like the Y and this is like the X. So, is my graph going up or down this time? Still going down, isn't it? And where do I start? I start at this E over R thing here. And I go down to here. But what's the slope equal to this time? Minus 1 over R. So the R is minus 1 over the slope. It depends on which graph you're using. Now in the earlier lesson when we did these graphs, which did we use? Did we put the V Here, or do we put the I on the y-axis? Was it, or was it this one? I don't even remember. Hang on, give me a second, I think. Hang on, I remember now. I, yeah. And the reason for that is because we said the voltage is like the thing that we change, so it goes on the X. So, I kind of prefer using this graph, but a lot of times in the exam, I think they have you draw this graph, and the reason is quite clear. This graph has two advantages. There are two things you can easily see on the graph. You can easily get the OR, but you can also very easily get the E, because it's just where it crosses the y-axis. So here you can get the EMF, although here the EMF is not as clear. So actually for this lesson you prefer to do it the other way around. This graph is the one you want. But I'm warning you now that sometimes you might have to do it like this. Just read the question carefully. If you can write this down, the slope in each situation is most important here. Okie dokie. Continue? Not yet? Okay. Continue? Yeah, yeah. Just before we do, let me just fix what I said earlier. What way did I say the formula was written in the formula book? B equals EMF minus IR. Okay, thank you. Right, continuing now. So here's my graph. A circuit is set up as shown in figure 1, and the voltage is recorded and the current is recorded. Graph this. So you actually have a choice, appropriate manner. Because we want to calculate the R and the E, what would be the better graph to use? Where we put the voltage on the x-axis or the current on the x-axis? Current on the x-axis. Okay, so let's graph this together. Before I draw the graph, can you just copy the table in your book and we'll make the graph? that? Continue? Right, so let's make the graph. Let's do our best. Okay. So Siva, what did you say goes on the x-axis here? Current. Current, which is I, measured in amps. And Andek, what goes on the y-axis here?
TD.
Potential difference, which is measured in
V.
volts. Okay. Now, what is the smallest current? 0.1. Okay. And the biggest?
1.
Alright, so we'll go 0, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1. So that's 1 there. And 1, 2, 3, 4, that's 5 there. Okay, and Andek, what's the biggest voltage and the smallest voltage?
Biggest is 1.9 and smallest is 1.
1 to 1.9.
Yeah.
And it goes up roughly in what units? Like 0.1s, 0.2s? 0.1. It starts at 1.
Starts at 1 then continues by 0.1.
Okay, I'll put a 2 here. I'll put a 1 here. This is 0.5.
But it starts from 1.
Yeah, but I think because I don't think I'll skip the 0 to 1 because I don't think it's necessary because I can still get a pretty big graph here. It starts at 1, so I still think I'll be fine if I put it in here. I don't like skipping. I only had to skip last time because it would have been so small, the graph. I prefer not to. Okay. Right, what's the first value? 0.1 current. Now what's the first I?
1.
I starts at 1, okay. And the voltage for 1?
1.
Oh, 1, 1? Okay. Next I is it 0.9? And the voltage?
1.1.
1.1. Okay. And next?
0.8.
Yeah. 1.2. Sorry, look, this is already off the charts. 1, 2, 3, 4, 5, 6, 7, 8, 9, 1. 1, 2, 3, 4, 5. Huh? What? Oh, sorry. Oh my goodness. Sorry. That's 1.5, not 1.75. That's 1, that's 0.5, that's 2, 1, 2, 3, 4, 5. Okay, let's try that again. Right, so I start off here with 1, 1. Right. Next one? 0.9 and... Okay, next one?
0.8. 0.2.
Next one?
0.7. 1.3.
Okay, next.
0.6. 1.4.
I see a pattern here. The next one 1.5 by any chance?
Yeah.
Okay. 1.6? 1.7, 1.8, 1.9. Okay. Look at that beautiful graph. Where does it cross the y? It crosses at 2, it looks like. So that means the E is 2 volts. Now what's the slope here? That would be minus. Here to here is 1 unit. And then here to here is 1. So the slope is minus 1. So what does that make the R equal to? R is equal to minus the slope. So here R would equal 1 ohm. So that's my R and that's my EMF. It's a nice enough question, isn't it? It's like the IV characteristic curves. Continue? Need a minute? Yeah. Work of art, isn't it? Yeah. Of course, in the exam, you'll be using graph paper. All right. Siba, Kim, continue. Siba? Yeah. Okay. Right. So I've answered that. So the good thing is, in the exam, you really only get two types of questions on this. The first type is they ask you to make a graph, and the second type is this. They give you a battery with EMF E and internal resistance R. And again, you're looking for E and R. And there's a resistor of 2 ohms, and an ammeter is placed in the circuit and reads 500 milliamps. The resistance is increased to 3 ohms, and the ammeter reduces to 400. Find the R. Now I'll just draw this to remind you of what it looks like before you write it down. So it's like the picture I think we did at the start, okay? You have a battery, and the battery has an EMF, and it also has an internal resistance here, okay? Then what you do, you connect this up to some external resistor. You know, it could be a light or a toy or whatever. So we'll call that resistor big R. And then you need to measure 2 things. You need to measure the current, so we'll use an ammeter, and we have to measure the voltage as well. Now remember, we said you can put the voltmeter here, or you could actually put it here. They should be the same. So I think this time, just to be a bit different, I'll put the voltmeter around this guy. Doesn't really matter. Really doesn't matter. Now, we can use Kirchhoff's loop rule, but we already have the formula from earlier. Kirchhoff's loop rule gave us the formula V equals E minus IR. Now, what do we not know here? We don't know E and R. So what's happening here is I'm giving you some information. I tell you, when you use a resistor of 2, the ammeter is 500 milli. So if, is this the formula I gave you earlier? Yes. So I guess I did need to give you that other one too. Anyways, let me write the info down. If R equals, if R equals 2, then the current is 0.5 amps. And then I also tell you, if you increase the R to 3, if R equals 3, then the current is 400 milliamps. So that's 0.4. Okay, so before I continue, I'll just let you copy this much down, and then we'll figure out how to get the E and the R.
We've drawn the diagram as well.
I think it's good to draw it again, since you didn't remember it at the beginning. Let me see the formula book. I thought the other formula was in it too. Now, there's actually one thing that I have in the picture that I really shouldn't have for this example. Can I just flick back to the question? So if you look at the question, there's something I don't mention here. A battery with an EMF E and internal resistance R powers a resistance of 2. The ammeter reads 500. And when you change the resistor to 3, the ammeter reads 400 milliamps. What did I not mention here that I have in my picture? A voltmeter, right? So it's kind of like this guy is off nearly, or you're not using it. So in this formula, which letter should I replace? It's not really appropriate to have. Which guy here should be replaced? I should replace this V, shouldn't I? Because we don't really have the V. What would be suitable to replace the V with? I or. Now, be careful, which or? Small or big? Big, good. Now let's recap. What don't we know now? We don't know the E and we don't know the or. Do we know the I? Yeah. We're given I measurements. Do we know the or? Yeah. So this formula now, together with this, what will happen? What maths problem will I get? Not quadratic, the other one simultaneous. Because how many unknowns are there? 2. And how many equations can I make? I can make 2 by using these 2 pieces of information. So I can say I or equals E minus I or. So I can say E minus a half or equals 1. I can also say I or equals E minus I or. So I can say E minus 2/5 or 0.4 times 3 is 1.2. 1.2 is 6/5. Okay. Now, what's the best way to solve these 2 equations here? Elimination. In fact, you already have one of the variables the same, the E. So I'll just minus them. Minus, okay? E minus E, gone. Minus a half minus 2/5. So minus a half plus 2/5. So what's that, Siva? Thank you.
Minus 1/10.
Okay? And then 1 minus 6/5 is minus 1/5. So you get R equals 2 ohms. And how can I get the E? Sub it back in. Do you see this one here? Looks like the easiest one to sub in. So I can get E minus a half times 2 equals 1. So in this example, what does the E equal? 2 volts then. Okay. So, in the exam, you have 2 types of questions here. The first one requires the use of a graph to find E and or, and the second one requires simultaneous equations to find E and or. Normally, the section A question on EMFs are this, simultaneous, and normally the section B question on EMFs are the graph. Obviously, because of the time in the graph paper. Okay. Right. So there's only the 2 possible questions here. How many questions did I give you in the book here? Probably 2. see. Ah, of course, why 2 when I can give you 3? Let's see. 2, no 2. Yeah. By the way, both of these were very similar to exam questions. Like number 1 was a section A from like last year maybe, and number 2 is a section B from a long time ago. Plus I added in a couple of my own parts as well, because you see it goes to A to K. Okay, so yeah, there's a few minutes left. So for about, I don't know, 6 or 7 minutes, you should be able to at least do number 1 and maybe even start number 2. Can I close this? Did you look at?
No, I left page empty.
You skipped one. Hate when that happens.
Yeah.